Thanks for joining me. We're going to be continuing our discussion on electron configuration. In the previous video, I went in a lot of detail on the background of electron configuration, and most of that is not stuff that I will ask you about. Now, the video today, this video is going to be a lot more of what you have to be able to do on my test. So hopefully by the end of this, you will know how to write an electron configuration and understand what each of the letters and numbers mean. So when we do electron configuration, I teach what is called the filling order of the electrons in an atom. And you'll be able to use a periodic table to kind of guide you through this once you understand how the periodic table is set up. Now, perhaps you remember from the Bohr model of the atom had these little rings around them. They were called orbits in the Bohr model, and they each held a certain number of electrons, like 2 in the first ring, 8, 8, 18, and so on. And we're going to see how that actually blends rather nicely with the quantum mechanical model, except they're not in a fixed orbit. Instead, they're going to be in a probable location called an orbital. Now, a typical periodic table looks something like this. There are different regions on the periodic table, and I'm going to label those, and you're going to have to know where those are. First of all, I've numbered the different rows, 1, 2, 3, 4, 5, 6, 7. So there's 7 rows on the periodic table. Don't worry about these 2 at the bottom. You'll see they actually fit in right in here in between rows 6 and 7 going horizontally across. Now, this first region that I have in white is called the S block. Now, helium, this element over here, actually fits right here. It's really, we'll learn, a 1s2 electron atom, but it gets moved over to here because it acts like the noble gases, right? I call it the Paris Hilton element, right? Paris Hilton grew up with a tremendous amount of money. She should have a lot of class, and that's not the way I see her necessarily. So this is the S block, these 2 columns over here. Then you've got the P block in pink, okay? And then in the middle we have the D block. Now it says N-1, and I'll comment on that right now. If you're in the first energy level, this would be a 1s1. You can imagine that this one actually fits here. It'd be, we would say 1s2. Then we come here, 2s1, 2s2. Kind of like you're in the S section of the stadium, in the second row, in the first or the second seat. Then you could go, after the 2s2, you go to the 2p1, 2p2, 2p3, 2p4, 2p5, 2p6, 3s1, 3s2. 3p1, 3p2, 3p3, 3p4, 3p5, 3p6, 4s1, 4s2. Now I know you want to call this one 4d1, but what the n-1 means is they're off by 1. So this is actually, even though it looks like it's in the 4th row, 3d1, 3d2, 3d3, 3d4, 5, 6, 7, 8, 9, 3d10, and then we're back to the 4p1, 4p2, and so on. I'll continue. And then of course we have the F's. They're down here, and they're 2 off of where they look like they belong. And I'll talk more about those once we get into this discussion a little bit. So I've already labeled these. This is the 1s region, 2s, 3s, 4s, 5s, 6s, 7s. Then when we come over here, see how this is in the second row? 2p, 3p, 4p, 5p, 6p, 7p. I told you the D's are off by 1, so this first row is not 4D1, but 3D, 4D, 5D, and 6D. And this top row fits right here, right in between 6S and 5D, and it's off by 2, so we're going to call that one kind of, so it's like it's in the 6th, but we're going to call it 4F, because it's off by 2, and 5F. Okay? Now that's important that you know those regions, okay? That's very important that you know those regions. The S, the P, the D, and the F region. All right. So watch as this thing animates for us as we go through this, right? Now remember I told you helium really fits right over here but it got moved here because it's a noble gas and it has properties similar to a noble gas. But when we fill these in, they go 1s1, 1s2, 2s2, 2p1, 2p2, 2p3, 2p4, 2p5, 2p6, so on. See how they're going in order? 4s1, 4s2, and then the D's are off. 3d1, 3d2, 3d3, and so on. 4p1, 4p2, 4p3, 4p4, 4p5, 4p6, 5s1, 5s2, 4d1, 4d2, and so on. So you can see how that pattern is repeating itself over and over and over again. Now, the 14 elements at the bottom would have fit right in here, but it turns out they have special properties because they have these f orbitals, so they've been separated from the main block of the periodic table. So when we look at this, lanthanum would be 5d1. That would be this element. And then following it, 4f1, 4f2 through 4f14. Then 5d2, 5d3, and so on. Then we get back 6p1, 6p2, 6p3, and so on. And of course, the same game happens down here. Actinium fits right here is the 6d1. And then the next element, rutherfordium, is 62. But in between here, we would fit all of these. And these would be, they should say 5F. It looks like this is a typo here. This says 6D2. That's clearly a typo there. That should be 5F1, 5F2, and so on. All right. Some of you are starting to see the pattern. You're not comfortable with it. I understand that. But you're starting to see when I say 1s2, 2s2, 2p6, 3s2, all I'm doing is reading off the chart, right? If I want to get to sulfur, it goes in order. It always goes the same order. You got to go through the first energy level, 1s2, and use those first two elements. Then here, 2s2, use those two. Then 2p6, use all 6 of those electrons. Then 3s2, use these two. And if I want to get to, well, chlorine, then it's 3p1, 2, 3, 4, 3p5. And that's what an electron configuration is. Now it's all based on the mathematics of Schrodinger's equations and the S and the P and the D. Those refer to what are called orbitals. Those are the mathematical solutions or the probabilities of where the electron will reside in the atom. Now it turns out we actually now in the last few years have been able to photograph these electron distributions inside an atom. And it turns out that that stuff they came up with in the 1920s, 100 years ago, is correct. That is what we see in a photograph of these things. Now, some of you are wondering why are the the S's are in order, the P's are in order, but why are the D's and F's off? Well, look, here's my best analogy I can give you. Excuse me. We're looking at the nucleus of the atom on the bottom. Okay, it's down here on the very bottom. So closest to the nucleus, n equals 1. That corresponds to the first ring on the Bohr model, right? If you're drawing rings or circles around the atom, this corresponds to it. N equals 1. That's its quantum number. It only has an s orbital. Then, when you get to the second energy level, we have what are called s and p orbitals. It's kind of like a sophomore in chemistry could take regular chem, we'll call that 2s, or they can take honors chem, 2p. It's a little bit more complicated, isn't it? And a little bit harder. Well, a 2p, even though they both, 2s and 2p, both reside in the second energy level, 2p has a little bit more energy. When we get to the third level, n equals 3, we have s, p, and d. And p is higher than s, and d is higher than both of those in terms of energy. Now, if we're still using the analogy of high school, by the time we get to the fourth energy level, that would be the senior year, we got kids that probably want to just drop out. So we make up kind of what I'll call easy classes for them to teach. I won't name any of them, but can you see how you could be a senior in your fourth year and the classes that you're taking, the 4S, are actually easier than what you might be taking as a junior, the 3D? So they go out of order. So when we start to do the filling order, imagine this is water filling a bucket. It's going to go 1s2, then 2s2, 2p6, 3s2, 3p6. After 3p6 comes 4s2, and then 3d10, then 4p6. So this is sort of giving you what we call the filling order. Kind of explains it a little bit better for you. This is the same thing, except now I'm adding on each s orbital, there's going to be, in each energy level, excuse me, the 1, 2, 3, 4, 5, there's going to be a single s orbital. So I've shown that with a pink circle. Right? So there's only one 1s orbital. There's only one 2s orbital, one 3s orbital, one 4s orbital. When we get to the p level, when they're available, there's always 3 p orbitals. So in the second energy level, there are 3 p orbitals. Each of these will be capable of holding 2 electrons, which is where we get 2p6. Then the d's can each hold 5 electrons, and the 5 orbitals, excuse me, which can hold 10 electrons. And then the f's, there's 7 f orbitals, each capable of holding 2 electrons, which is why on the very bottom of the periodic table there are 14 elements going across. Those 14 elements correspond to 2 electrons in each of these 7 orbitals. The 5 d orbitals, each can hold 2 electrons, represent the 10 electrons that you get in the center section, the d section of the periodic table, right in here. Then of course the 3 p orbitals can hold 6 electrons, and that corresponds to the 1, 2, 3, 4, 5, 6 going across here, the p block of the periodic table. All right. Now there's certain rules that apply in doing and writing electron configurations. The first one is called the Aufbau principle. It's a German word meaning building up. Look, if you go to Disney, right? Maybe after COVID's over you want to celebrate and go to Disney, right? You're going to go, maybe you'll drive down there and you'll park in the gigantic parking lot and they'll have Goofy, right? And Goofy will be directing the first car to park in a spot here, and then Goofy, the second car parks here, and so on. Now, if you decide that you don't want to follow Goofy's recommendation and you want to park wherever you want, all of a sudden Goofy is not a fun little character. He's like a wild animal and gets pretty upset because you're messing with the Aufbau principle, the building up order. You have to go in order. And that's why we always can say 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. I've done that 10,000 times, so it's really easy for me. So the Aufbau principle says electrons are added one at a time to the lowest energy orbital available until all of the electrons have been accounted for. Okay? Now, again, they go in order is what the Aufbau principle says. Okay? Now there's another rule, and the next rule that we need to know is called the Pauli exclusion principle. Now, what it says is an orbital can hold only 2 electrons, 1 or 2 electrons. But in order to occupy, that is to have 2 electrons in a single orbital, they have to be spinning in an opposite direction. It turns out when an electron spins, it creates a magnetic field. So think about my fingers as 2 magnets, North Pole, and if I hold them next to each other, they will repel. If I flip the magnets this way, so I'm going to call this one spin up and spin down, now they can actually attract. So electrons, even though they have the same negative charge, want to repel, but if they're spinning in an opposite direction, they will allow themselves to occupy a single orbital. That's called the Pauli exclusion principle. And then finally, the last rule that governs filling order is called Hund's rule. And it says if you have 3 equivalent p orbitals, every one of those orbitals gets a single electron before any one gets 2 electrons. So electrons occupy equal energy orbitals, so the maximum number of unpaired electrons results. In the previous video, I call this Hund's rule the urinal rule, or the creepy guy in the bus rule. For the guys, hopefully this makes sense. You got 3 urinals, and they're available. Should you use the middle urinal? No, because then somebody's going to have to come right next to you. So you use the one on the left, the next person uses the one on the far right, and the third person, if we were in class, somebody would say they just have to wait. Nobody says both guys should be using the same urinal simultaneously. That just doesn't happen. right? Now, for the girls, creepy guy on the bus says, you're riding a bus late at night. You're the only person on the bus. There's 24 additional seats on this bus. And the bus stops, picks up an older gentleman, and he decides to sit right next to you. Unacceptable, isn't it? Right? Because there's a bunch of other seats that Electron can occupy. And according to Hund's rule, you're going to try to fill the maximum number of seats before anyone has to double up. Okay? All right. So let's look here. This is kind of a Bohr model of a diagram with a cutaway showing those little rings, kind of like an onion, I suppose, right? Where you get 2 electrons in the first energy level. A little dot represents a nucleus, then 8, 8, 18, 8, and so on, right? Now, if we were to look at this, now I've expanded my diagram. So what we're looking at is on the first energy level is a 1s orbital, and that's all that's available. In the second energy level, there are 2s, 1 2s orbital, and 3 2p orbitals available. When we get to the third energy level, there are s and p. Now, the 3ds actually are coming from the third energy level, but they're so high energy, they end up being in between a 4s and a 4p. Now, if we accept this model, then when we put electrons in, they're going to be like water filling a bucket. So if you can imagine this has been a bucket and somebody's drilled a bunch of holes in it, the water is going to pour out from the bottom hole first. And once the water is enough, then it'll fill up here. So look at the order. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d10, 5p6. So I'm just simply going in order from the bottom up. Now, when you're in class, I will be pointing to the periodic table and saying these, and it's going to make even more sense to you. Okay? Now, let's compare the Bohr diagram that I've shown here, okay, the simple Bohr diagram, with the energy level diagram and then the electron configuration. So if I want to do hydrogen, okay, hydrogen's electron configuration is 1s1. Now, let's look at the periodic table for a second, just so you can see. Well, this mouse is lagging a little bit. Let's see. Okay. Hopefully that's going to make it bigger for you. All right, good. So do you see over here, we got in the first energy level, that's 1. We're in the s block, and it's 1 electron in. Hence, that is a 1s1 electron configuration.